So today we're going to look at capacitors. They're another device, passive electronic device like the resistors, and they come in a bunch of different types. So we have some ones here. These ones here are non-polar capacitors, and we have these two that are polar capacitors. These ones in cans are called electrolytic, and since these ones are polar, you have to actually put them in the circuit the right way. So the long lead is usually positive, the short lead is usually negative, and they usually mark the negative lead with a big white stripe like that with minus on it. So it's usually pretty easy to figure it out. So those have to go in the circuit one particular way. These go in the circuit in many, many different ways. And capacitors do a couple of things for us. They can do, they basically are a device that stores electricity for a brief period of time. The larger a capacitor is, the more electricity it can store for a longer period of time. And we use them for doing things like storing electricity. We can also use them to filter electricity. So let's look at the storing electricity part of capacitors. I have a little circuit here. It's very simple. It's just a little push button switch which runs through a current limiting resistor to an LED. So I push the button, the LED comes on. Okay, and if you notice, if I let go of the button, the LED turns off pretty much right away. So there's no electricity being stored there. It just turns off. So if I put my capacitor here, now this is a polarized capacitor, so I have to put the positive on the positive side and the negative going over to the negative here, like so. Now when I push the button, the capacitor charges up, and when I let go, the light takes a little bit of time to dim. Like that. And that's because when I push the button, the electricity flows through our LED, but it also flows into this capacitor and it stores it. And then when I let go of the button, the capacitor lets the electricity go and it keeps the light running for a little bit longer. And that's how that works. Now, the size of the capacitor matters. This is a slightly smaller capacitor in terms of its capacitance value. This is a 1,000 microfarads. This is a 220 microfarad. It still lights up, but it dims way faster. That's because this one gets rid of its electricity. It can't hold as much electricity, so it gets rid of it way faster. One of these even smaller capacitors, this one's about 10 nanofarads or so, we don't even really notice a difference because it just doesn't hold enough electricity to keep the lamp lit for us to notice a difference with our eye. This ability to store electricity is used a fair bit for capacitors in various ways, for like timing circuits and that. And it's a very important use that we use them today for in the modern era, is that we use them as computer memories. So when you have your dynamic RAM is just millions and millions and millions of microscopic little capacitors all connected together with logic that remember everything in our computers these days. So that's the storing electricity part of capacitors. Okay, so we're going to look at the filtering, how capacitors help us do filtering. And I have a little, it's not much of a circuit. Right now there's a capacitor, but it's not in the circuit yet. What we're looking at here is I've got my function generator hooked up here, and it's generating a 60 Hertz sine wave like this. Now we can see, I've left channel 2 on so we can see where ground is easily. It's an AC signal, so this is basically 4 volts of what's coming out, what would normally be coming out of your wall at 120 volts. So it's an AC signal. And capacitors will allow an AC signal to pass. So if I take this and plug it over here, the signal is still the same. It doesn't change. So it's going through the capacitor. Capacitors, however, do block DC current. They won't allow DC electricity to go through because it's not changing. So what we can do with a capacitor then is if we have AC with a DC component. So what I can do is I can adjust my function generator to put a DC offset on this. Right about there should be good. So now the 0 point of where this thing should be right down the middle here, but ground is down here. So there's a DC component to our AC electricity, which can mess things up. And what the capacitor does is we take this and we plug it into the capacitor. We now see that it's right back down to where it should be. And that's because our capacitor here is filtering out the DC component. It's still there. I can put this back over here and we'll see that's still there. It's just that the capacitor is getting rid of it. And so that's one of the filtering things that capacitors do, is get rid of a DC offset of a AC signal. Okay, now we're back and we're in a little different of a setup here. I have the AC signal with the DC offset coming in. I've reduced the amount of the AC signal because of what we're simulating. We're kind of simulating that we've rectified our signal AC to DC, and now we've got a bit of what's called ripple. And in the previous, we saw that if we put a capacitor in series with an AC source, it goes to the DC component. So what I have here is I have a capacitor that's hooked up in parallel with the circuit. However, it's cut out because of the switch. If I push this switch in, it'll bring the capacitor into the circuit in parallel. And what that'll do is, well, let's take a look. We'll push the button, and it gets rid of it filters out the AC. We're now just left with a nice pure DC signal. So one of the other things capacitors can filter out is AC if you put them in parallel. And there it's filtered out our AC, because what's happening is the capacitor is when the AC is up, when the AC is up higher, it charges, and then when it drops down, it then discharges and keeps it at a constant level. So if we do that, push that button, see, you get a nice little DC line there. So that's the other filtering aspect of capacitors, is that if we put them in parallel, it'll filter out the AC and leave us with DC. So capacitors can also, like resistors, can also be a network. So I have here two capacitors, and my multimeter does have a capacitor setting, so I can measure these. And if I measure my first one, so these two are in series, but right now I can measure my first one at, looks like about 16.7 nanofarads, and my second one is at about 9.1 nanofarads. So this is about 16 and 9 nanofarads, and we can put these in series like this, and we can measure across the series, and we end up with 5.85 nanofarads. That's kind of interesting. With resistors, we expect the numbers to add. They didn't this time, so we'll have to look at that. Okay, so we have our two series capacitors like we had before, and we can put our measured values in. So we have 16.7 nanofarads and 9.1 nanofarads. And our total capacitance, as measured, was 5.85 nanofarads. Now, if we're using resistors in series, these would add up to 25.8, but we didn't get that. And the reason for that is that capacitors work opposite of resistors. So if I have 1 over C1 plus 1 over C2, 1 over however many capacitors I have is going to be 1 over the total capacitance. So let's see if that's what we got here. So we have 1 over 16.7 nanofarads plus 1 over 9.1 nanofarads. That gives us 1 over 0.16977 nanofarads, which, once we divide 1 by that number, we get 5.89 nanofarads, which is pretty dang close. So capacitors work opposite of transistors, at least for a series, in that we have to do this 1 over capacitance to do the math. So let's take a look at if they're in parallel. Now I have my same two capacitors, 16 and 9-ish nanofarads, and I've put them in parallel. So they're in parallel. So if I check the capacitance now, we get a capacitance of about, oops, the meter's having some issues here. Let's try that again. About 25 nanofarads. So in this case, they were in parallel, so they just added up. So we have the networks work kind of the same way as resistors do, except they're flipped. So if they're in parallel, we simply add the capacitance, and if they're in series, we have to do the 1 over the capacitance little trick. To show that this actually works even further along, take this guy in here, plug this guy in here, and this guy looks like about half a nanofarad, or 530 picofarads, and now he's in series with this parallel thing, which is about 25, and we end up with about 0.52 nanofarads for the whole thing. So you can see how that works out. Okay, so let's look at our two capacitors in parallel. We have our one capacitor at 16.7 nanofarads, and our other capacitor at 9.1 nanofarads, and they're in parallel, and we measured the total capacitance at 25.8 nanofarads. And just looking at that, that shows that when we have capacitors in parallel, we actually just add them up. Okay, so this is again opposite of what we have for transistors. And we can just put our numbers in, and so we have 16.7 nanofarads plus 9.1 nanofarads, and those added together are 25.8 nanofarads. So it works out just fine. So when you're doing capacitor networks, it's just simple, it's just like resistor networks, except we flip them. And we saw that when we did our second example, where we had a parallel and series circuit, which we'll look at here in a second. So here we have our parallel series capacitor circuit. Again, we still have our 16.7 nanofarad capacitor here, and our 9.1 nanofarad capacitor here, and this one here is at 0.53 nanofarads. We'd actually normally say 530 picofarads, but we'll say this keeps everything in the same units. And we, as we measured in our last little look, this all comes out to 25.8 nanofarads. So that's our resistant effective capacitance here. And now this is just as simply as 2. So this is parallels now being reduced to its net capacitance. And now it's just a series circuit. And so we now have, again, because the series is like this, we have 1 over 25.8 plus 1 over 0.53 nanofarads. I should probably put my units in there. Here we go. Which gives us 1 over 1.9255 nanofarads. We do our math there, and we get 0.519 nanofarads. Pretty dang close. So we can, work out capacitor networks just the same we do as resistor networks. We just have to remember that capacitor networks use the same formulas, just backwards. So what we would use for a series bunch of resistors in series, we would actually use 1 over for series capacitors, and for what we would use for a resistors in parallel, we actually for parallel capacitors, we just add them up.